So welcome to this lecture on the theory of non-blocking algorithms. So what we will see in this lecture is that to design an algorithm that doesn't use locks, there is a lot that we need to understand in terms of the way that the memory operations interact with each other and how we can write and design such an algorithm correctly. That is the main focus of this chapter. So we'll start with by saying that we are only interested in memory operations, which are read and write operations. So the rest of the operations are internal to a CPU, so we are not interested in them. It's only the read and write operations that actually have a cross-core interaction, and that is what we are interested in, right? Primarily in this section, whenever we discuss memory models, this is something that is of paramount importance to us. So every operation has a start time, an end time, and a completion time. Let me explain with an example. So let us say that this is a read operation where I'm reading something from the memory system. The memory system would basically mean the L1 caches and beyond. But as far as the CPU is concerned, it's a single physical memory system. You send a read to it and you expect a value in return. So if I do that, then there will be a point of time at which the read operation was issued, in the sense it left the pipeline, it went to the memory system. That is the start time of the operation. The end time is when it has kind of come back and it has left the pipeline, or where it is deemed to be completely processed. That is the end time. So for every architecture at the hardware level, you can define the start time of an operation and you can define the end time of an operation. All right, so this is definable. At some point, the operation actually completes. So what is completion is a rather tricky question. But in the case of a read, it is somewhat simpler. It's at least way simpler than writes. It is basically at the point at which it gets the value and the value cannot subsequently change. So what happens? When you send a read, it goes down to the caches. In the caches, a read happens. And then at some point of time, the value is finalized. The value may not have come to the CPU, but what is rather clear is that the value is henceforth not going to change. So the value has been locked. So we can think of that as the completion time. And then, of course, the value finds its way back to the CPU. And finally, the operation ends. So this means that at some point, you actually have the completion time of the read, right? Where you lock the value and then the value comes back and the operation finishes. So in the case of a read, it is kind of straightforward that the start time is less than the completion time, which is less than the end time. Of course, the completion time is not known, or in most cases is not known. Of course, if you are a hardware designer, then you would know at exactly what point this happens. But if, let's say, you're just running a program and looking at its values, then you don't have a way of knowing. But you can be rest assured that there is a point at which this completes, which means the value is locked or it cannot subsequently change. So this, for a read operation, here are three simple concepts. So let us now look at writes. When we consider write operations, the situation actually gets far more complicated. So what happens in the case of a write? It is like dropping a letter in a post box. So you never know when it's going to reach. So in this case, the write is simply deposited in the memory system. And the memory system is a rather complex beast. So what you have here is that the write actually even doesn't go to the caches, it goes to what is called a write buffer. So write buffer is like the small buffer of recent writes, where if subsequent writes come to the same cache line, they are all merged. Because the cache line is 64 bytes and the granularity of a write is only 4 bytes. So you are providing an opportunity for merging. Gradually, they get drained to the cache and then they reach the caches of other cores. that can take its sweet time. So this basically means that if I consider a write operation, I will have a start time, which is again when it is deposited in the memory system. The end time obviously has to be when the write exits. When the write exits my pipeline, which means when the pipeline forgets about the write, then you can say that the write has ended. But the question is, when does it actually complete? So in this case, let's say if I'm depositing a letter in a post box, so the start time could be when I left my house. The end time could be when I came back. But the actual completion time is when the letter reaches the destination. And in this case, the write has to make its way through the write buffer, through the caches and whatnot. And of course, through an on-chip network until it reaches the destination, which can happen either immediately or can happen much, much later. All right. So it is very well possible that the completion time is sometime in the future. All right. So in this case, when you don't know, there is a wide spectrum of possibilities, which is why we have to define some sort of a contract or some sort of a specification. So whenever you define a contract, what happens? There are two parties or multiple parties. Every party adheres to whatever is its part of the contract, such that the entire system functions seamlessly. So in this case, some specification or contract has to be drawn out between the program, the programmer, the compiler, the hardware, and threads running on different cores, such that everybody knows what to expect. Because in this case, the write is completing at some point, right? So we have to know what to expect, what is intuitive and what is not intuitive. And of course, this argument can be generalized to any operation on a concurrent object. So memory is a concurrent object. Why? Because it allows parallel or concurrent reads and writes. Multiple threads can read and write together at the same time. So we can think of the memory which is presenting itself as an array of bytes, as a concurrent array of bytes, where I'm reading and writing. But of course, given the complexities that I just explained, it will not work in the way that you think it should work. Nothing stops me from extending the definition to a concurrent queue, a concurrent stack, a concurrent linked list, given that memory, which is a concurrent array, has these issues. I can have a concurrent queue which supports two operations, NQ and DQ, right? Again, in the case of NQ and DQ, we'll have the same. We'll have a start time, we'll have an end time, and we'll have a completion time. So which means if the end means that the thread that issued the NQ knows that NQ is done from its point of view, but it may not be done like from the point of view of other threads. Other threads have to wait for the completion time. All right. The same holds for a stack, the same holds for a linked list, everything. So we need to define something, right? It clearly means that some specification or some set of rules have to be defined to control and discipline this process. So the first thing is, if I were to draw a timeline, I have a start time, I have an end time. As I said, the completion time can be at any point after the start. Let us say that this is my rule. If I have a single completion time, in the sense all the threads agree that at this point of time the operation completed, everybody agrees, there is unanimous consensus, then we say that the operation is atomic. Atomic means it appears to execute instantaneously at the completion time. Let me repeat. An operation is said to be atomic when it appears to execute, the key word here is appears, to execute instantaneously at the completion time. And it is not possible to observe any intermediate state between its starting and ending. Let's say that in the case of a queue, NQ, it goes through intermediate states, where you change different aspects of its state, but all of that is not visible. So others either see the operation is done or it is not done. which means the entire operation in a certain sense appears to execute instantaneously at this point, which is the completion time. All right. So this is also known as atomic. The completion time does not have to be explicitly known. All right. So the completion time can be implicit in the sense that all that you can say, like a mathematician, that a completion time exists, that a single completion time exists. Everybody agrees on that single completion time, but I don't know when it is. Right? Insofar as I am concerned, it exists. Just proving mere existence and proving that all the threads agree on that time is good enough. Right? As far as atomicity is concerned, because atomicity says exactly this, that even if the completion time is known or not known, it doesn't matter. It needs to theoretically exist, and the entire operation needs to appear to complete instantaneously at this point of time. All right, so this is what is called atomic. If a system is not atomic, as is the case with many architectures, many server class architectures, so ARM version 7, which runs on our phones, that used to be non-atomic, and many others also. In that case, it appears that it has completed at different instants to different threads. They don't agree on a completion time. So it appears that thread 1 may think it has completed here, thread 2 here, thread 3 here, thread 4 here, so on and so forth. They do not agree on a completion time. That is non-atomic. But thankfully, a large number of recent architectures, and so this holds for concurrent systems theory. So it holds for both hardware as well as software. It's a general concept. Thankfully, for many recent architectures, they are atomic or they are designed to be atomic. So let us now look at this in the context of a concurrent queue. So assume I have 3 different threads, they're enqueuing and dequeuing. Whatever I'm enqueuing, that is the value that I'm entering into the queue. If I dequeue something, whatever I read, that's the value that I'm reading. So then, there is a parallel queue, I just run them. So then my threads will always enqueue something, there will be some value. They will dequeue something, there will be some value. Just by analyzing the values, the question is, what can I do? So first assume that the completion times are known. How do I know? That doesn't matter. So the key thing is that if I organize them, every operation of a thread, so the first thing is that if you consider any single thread, you have a start, you have an end. So you clearly cannot start the next operation until the previous one has ended. This holds for a single thread. You cannot initiate something until the previous one is finished, because a single thread is sequential, it's not concurrent. So you have start, you have end. Now, what we have done in this case is that we have assumed that, so we have given it a set of outcomes, and we have assumed in the first case that we know the completion time somehow. How we know? Well, that's not a question that you will ask, but let's say we know the completion time somehow. So then we have NQ1, the state of the queue is 1. We have NQ3, the state of the queue is 3, right? NQ2, DQ1. And I have just arranged all of these events in the order of their completion times on a linear line. Is that clear? That I was somehow aware of the completion times. I arranged them on a linear line. So I can think about this situation like this, that there is a hypothetical thread that sequentially processes all these events. All right. So the thread does first what? It enqueues 1. So the contents of the queue are 1. Then it goes to the next completion time, which is NQ3. The contents are 3 and 1. Then it goes to the next one, which is DQ. What will you DQ? You will DQ the head of the queue. You will get back 1. So the contents are 3 and this result is correct. Then you will DQ again, which is 3. So then you will DQ 3. Why? Because that's the only element and the queue becomes empty. So this result is correct. So on, and then you will enqueue 2, so you will have 2 in the queue, so on and so forth. So what is the key idea? The key idea is that if I know the completion times, then I can arrange all the events in ascending order of their completion time. And I can think of it that one hypothetical sequential thread is actually executing all of these events. Correct? Now the question is that if I execute all of these events, is it following the semantics of a queue? Correct. So what is the semantics of a queue? First in, first out. Right. So queue, you enter your first in, first out. The head of the queue is the first to be serviced. If this is following the semantics of a queue, then this sequential execution is called a legal sequential execution, because the moment something is sequential, you can just see whether the results of every operation are correct. In this case, the execution is said to be legal because it is correct. So what have I done? I was somehow aware of the completion time. I organized all the events sequentially in the order of their completion times, ascending order. I assume that a thread is simulating all of these events, a sequential thread, where the events were originally issued by different threads, but I don't care. And then if this sequential order is legal, then I will say that a parallel execution, which is the one on top, so this is your parallel execution, is equivalent to a legal sequential execution, right? Where this is how I establish the equivalence. All right. Now, assume that I am not aware of the completion times, which is closer to reality. Start and end, I know. Start is when I issued the enqueue, end is when I return from the enqueue. Start and end, I know. When it completed, I don't know. The question now is, can I guess completion times where the completion times follow a certain property? What property we'll just discuss in a minute. Where if I guess the completion times and establish an equivalence the way that I'm doing here, a parallel execution is equivalent to a legal sequential execution. All right. Is this part clear? Now the question is that when I'm not aware of the completion times, how do I guess it? All right. So let us say I have some algorithm to guess it. Then what are my constraints? Can the completion time be anywhere? Or are there any constraints on the completion time? Let us say that my constraint is as follows. My completion time of an operation is between its start and end, which means that for the DQ, the completion time is here between its start and end. For this DQ, it's between its start and end. Even for an NQ, it is between its start and end. If this is the constraint that I impose upon myself, even if I'm not aware of the completion times, if I can create an algorithm to somehow guess a set of completion times where it follows this property between start and end, I can still establish an equivalence between a parallel execution and a legal sequential execution subject to this constraint. All right. I'm not saying it is possible to do all the time. We'll see examples where it is not possible to do. But wherever it is possible to do, this is a specification. What are the elements of the specification? That for every operation, a single completion time has to exist, which means that the execution is atomic. Correct? So single completion time is atomic. All right. The completion time has to be between the start and the end. All right. So we'll give this some name. Let me just fill in the blanks here. Then if I arrange the events in the order of their completion times, the equivalent sequential execution is legal. All right. All three together, right? So, well, if it's between start and end, that's just a constraint. All three together, this specification is known as linearizability, which means that if a parallel execution is linearizable, it follows the three properties that I just mentioned. Or in other words, if you have a parallel execution, whatever it may be, a parallel queue, stack, linked list, or even a parallel memory, which is presenting itself as an array that can be concurrently accessed. Linearizability is the property that I just mentioned, which is a combination of atomicity plus the completion time being between the start and the end, and the equivalent sequential execution being legal, right? These three things. Then the property is said to be linearizable, or the specification is said to be linearizable, or you are said to be consistent with linearizability. Different ways of looking at the same thing. So this is, in a sense, a notion of correctness of a parallel execution. That if I say a parallel execution is correct, then I can, but then you will say, what does correct mean, right? Kindly define correctness for me. I will say that is a parallel execution correct as per linearizability. Then you will start searching for unique completion points within every operation such that the rest of the properties hold. So linearizability is good. It basically says for every operation, the unique completion time is between the start and the end. But this is okay for higher level data structures such as a stack or a queue, something implemented in software. But something like, just memory, linearizability is very hard to achieve. Why? The answer is very, very simple. The answer is that you have to wait for the write to complete. All right, which means it has to reach all the cores, then only you will release the write on the core that issued the write. Correct? Then only you will end it, which means you will have to maintain state for a long time. So this is very slow and hence impractical. It is practical for a higher level data structure that involves a lot of operations. But at a really primitive operation level, this is very, very slow and impractical. So let me now relax myself and allow myself some more flexibility. Let me now say that I will not go for linearizability, I will go for SC or sequential consistency. The sequential consistency model is atomic, which means for every operation, you have a unique completion point. But it does not have to be between the start and the end. It can be anywhere, subject to the fact that if a thread has, let's say, issued multiple operations, for any single thread, the completion times of these operations are in the same order as the operations within the thread. Is that clear? So if a thread, let's say any thread has issued operations A, B, and C, then A will have a completion time, B will have, C will have. We are not saying it has to be between the start and the end, but this condition has to hold. Is that clear? So which means you respect per thread order and you respect atomicity, and the equivalent sequential order is legal, right? This is sequential consistency, and we will explain this in a quick second, the differences between them by considering an example. If, let's say, you don't even want to respect this per thread order, because in a sequential consistency also what happens is you do not allow operations from the same thread to overtake each other. That's the main idea, right? If you look at this, this is exactly what this is saying. That operations issued by the same thread are not allowed to overtake each other. Those who have studied out-of-order processes will not be very happy with this, because what happens is when you have reads and writes, typically writes are sent a long time later when you are sure that this write is actually on the correct path, but reads are sent early. So the fact that modern processors kind of mix the order of operations and allow operations to even unrelated memory addresses to overtake each other is very common. Otherwise, modern processors will never get any great performance. That is why even sequential consistency is impractical. What is more practical is you don't even have the per thread rider. All right, you don't have that restriction. You be even more general, which is called weakly consistent. And weakly consistent does not impose this per thread restriction. It has some other restrictions we'll discuss, but not something as binding as the per thread restriction. So I'll look at some examples, but let me go through this slide first, then I'll show you an example. It'll kind of be clearer. So as I said, operation being atomic means a single completion time, which enjoys consensus. Everybody agrees that. Atomicity versus linearizability. Well, atomicity is a part of linearizability. Atomicity says that it completed at one point. It doesn't say when that completion happens. Linearizability says that it has to be between the start and the end. All right. Sequential consistency doesn't say it has to be between start and end. It simply says if a thread has multiple operations, if this is their order of operations, the same order is followed by their completion times. All right. So they say different things. You have different kinds of specifications. And so the linearizability defines this completion time is also called a linearization point in the literature of linearizability, which says it has to be between them. So this is the point of atomicity. And again, as I said, if you look at many theoretical algorithms, they don't precisely say that this is the point. It is sufficient to prove that such a point exists. All right. So we have, a full course in IIT Delhi dedicated to this. So as I said, sometimes if you think about it mathematically, in many cases, instead of telling you that this is the solution, I can just get away by saying that a solution exists. All right, it typically happens with matrices and so on. Right, if you look at the rank of the matrix, you can say solution exists, but you're not finding the solution. So in this case, if you say a point of linearizability or a linearization point exists, that suffices in most cases. So what we will do now is that we will look at an example and we'll come back to this slide, because an example we have kind of strayed too far without an example. So let us now look at an example. So there is a standard way that these are written. So let us say that x is a global variable which is initialized to 0, y is initialized to 0. All right. And I write 1 to x, and then I wait for a long, long time. All right, I wait for 6 months. And then the second thread reads x to be 0. All right. So what I do is I write 1 to x and the operation starts and completes. Starts and ends, not complete, starts and ends. And then I wait for 6 months. My program is running. I wait for 6 months. Then I read the value of x. Okay. Is this outcome? And I read the value of x to be 0. Is this outcome linearizable? So to check that is very easy. You draw the same diagram that we have been drawing. So let us say this is the operation wx1. And a long, long time later, you have the other operation rx0. Whatever is the completion time, it doesn't matter. The completion time has to be some point between the start and the end. Whatever is the completion time, it doesn't matter. It has to be after the start. And the gap between this and this is huge. So if I organize them like this is going to be wx1, this is going to be rx0. So is this legal? This is not legal. Given that this is not legal, this outcome is not linearizable. Right? So clearly this outcome is not linearizable. Is this outcome, so let me write linearizability, no. All right. Is this outcome sequentially consistent? Why is this outcome sequentially consistent? Again, let us draw the same diagram. So in this case, let the completion time of this be over here. But in the case of sequential consistency, there is no restriction that the completion time has to be between the start and the end. It can be arbitrarily after the end sometime. Or it can be before the start also in some architectures. Is this outcome legal? This outcome is legal because I'm reading the initial value and then I'm writing 1 to it. So this outcome is definitely legal. There is no per thread order that is being violated because every thread has a single operation. It is atomic. So this outcome is sequentially consistent, right? But so you can see if this is the execution, this execution is not an element of linearizability, but this execution is an element of sequential consistency. Is this simple illustration or illustrative example clear? If that is clear, we can go back to our slide where the start and end times are sadly not relevant in this case. What we instead have is a per thread order. What sequential consistency does, if you think about it, it interleaves the operations of the threads without violating per thread order. That is exactly what it does. Let's say these are my fingers, then I am not allowed to do this. This will violate per thread order. I do this, then I can interleave them. This is an interleaving, this is an interleaving, this is an interleaving. These are all valid interleavings. All of these are allowed. What is not allowed is doing this and this. All right. So that is exactly what this is an alternative way of looking at sequential consistency, where you are simply looking at interleavings. All right. Where you do not violate the per thread order, and then you can have any interleaving, and this is one such interleaving. All of them are fine, and they provide a way of reducing a parallel execution to a sequential execution. But the sequential execution should be legal, right? Legality is important because so how do you prove that a parallel execution is correct? What is even the criteria for correctness? The criteria for correctness is that you use one of them, parallel linearizability, SC. Using that, you reduce. So see whether it is satisfying their criteria or not. Then you can say it is correct as per linearizability, for instance. So let us look at sequential consistency once again. Consider this execution that is shown. Assume that x and y are global variables and they are initialized to 0. And t1 and t2 are local variables which are stored in registers. So what we are doing here is we have two threads. Thread 1 writes 1 to x and then reads the value of y. So these are memory accesses to different addresses. Similarly, thread 2 writes 1 to y and reads the value of x. So these are memory accesses to different addresses. All right. So the question is this outcome possible? Which means T1 is 0 and T2 is 0. See, it all depends possible under which criteria. Under sequential consistency, which we have said it has to be an interleaving, which means interleaving is either like this, or like this. It's clearly not possible because you can assume that with no loss of generality, let's say x is equal to 1 happens first. Whatever happens, ultimately you'll have y equal to 1 and then T2 is equal to x. For it to be a legal execution, T2 has to be 1. And so is the case for the other one. So because we cannot find an interleaving, it is not sequentially consistent. However, if you run this piece of code on any real machine, including this laptop over here, you will find this outcome T1, T2 equal to 0, 0 come. So in general, for a parallel program, you can have many different outcomes. So the outcomes that are allowed, that is actually determined by the memory model of the machine. So any memory model has a set of allowed outcomes and a set of disallowed outcomes. So in this case, you will see that T1, T2 equal to 0, 0 you are observing, which means that the memory system and the cores are not sequentially consistent, because sequential consistency is a good idea in theory, but in practice it extracts a very high price. And that very high price is basically the price of efficiency. So what happens is, if you want it to be sequentially consistent, this read over here has to wait till the write is done. But those who have studied out of order processors will agree that writes are typically sent when you are sure that an instruction is on the correct path. That reads are normally sent early for performance reasons, because they are often on the critical path. So you can't do this, so you will actually end up losing a lot of performance, which is why almost all modern processors tend to boost up these reads or send them early. If you send them early, it will not remain sequentially consistent, because what will happen in a real processor is that this read will kind of happen first, this read will kind of happen first, and then they will read 0, 0, and then there will be a problem. So that's all right. That is why sequential consistency is a theoretical model. It's not practically provided. And if it is not practically provided, then we need to have other specifications, other memory models. So we have seen linearizability, we have seen sequential consistency. So let's see a few more then, right? The ones that are practically implemented. But before we do that, we would like to understand that what is this game of sequential consistency and non-sequential consistency. So in general, what happens is that you define a set of instructions known as atomic instructions or synchronizing instructions, same thing, right? So let's say that your atomic fetch and increment is an example of that. Your compare and swap is an example of that. So any memory model, even if it violates a bunch of this reads and writes. So mind you, in this case, if it was a single thread, you could have happily reordered this read and write. There would have been no issue, right? Because they are two different addresses. Same address, of course, you can't reorder, but different addresses you can happily reorder. There is no problem. But when you consider this execution in a multi-processor context, then you have this non-sequentially consistent outcomes, right? In a single thread, it will not cause any problem. So which is fine. So modern memory models are actually weak memory models, which allow you to reorder accesses to different addresses, subject to the fact that if there is a synchronizing instruction, and so let's call it a sync instruction, and in the same thread you executed a set of operations, all of them have to complete before the synchronizing instruction completes. And after this, whatever succeeds this in program order in the same thread, all of them have to complete after the synchronizing instruction completes or synchronization instruction completes. In the sense that their orders of completion could be like this, which is fine. Similarly, their orders of completion could be like this, which is fine. But this one kind of establishes a fence that whatever precedes me in the same thread has to complete before me. Whatever succeeds me in the same thread has to complete after me. So this instruction is also known as a fence, and all synchronizing instructions have a built-in fence. Of course, fences can be of different categories, but let us consider this, which is the simplest type of fence. So this allows or creates some kind of discipline in the world of the chaotic world of memory models, where all the reads and write before it, if they are to different addresses, the processor can happily reorder them. But this discipline has to be followed, that if there is a fence, everything prior to the fence completes, then only the fence finishes, and nothing after it can begin. So it is clearly a very performance is clearly a very latency heavy instruction, but its job is very clear. Its job is to kind of separate accesses on both of its sides. So this is the role of a fence. So all weak memory models still have to support these fences, and any kind of synchronizing operation has to have fences. Now the question is, we have discussed many concepts. How do we connect them together? So we have discussed linearizability, we have discussed sequential consistency, which are theoretically good but not practical. And then we have discussed your fences, right? So they are all connected via a theorem. The theorem says this. So you need to connect them because, when you are running something, when you're writing parallel code and running it, you don't want it to run differently on a machine that, let's say, supports sequential consistency. You don't want to run it differently on a machine that does not support sequential consistency. You just want to write one program which will run everywhere, regardless of the underlying memory model, correct? That is what you want. Now, how will you ensure and enforce this? So you need some theory. So this theorem, which is one of the most important theorems in computer architecture and OS also, it says a very simple thing. So if you would recall, we had discussed a data race free program or a properly labeled program. What this said is that any access to a shared variable has to be wrapped in a critical section. A critical section has a lock and an unlock. The locks, the additional thing that I'm telling you now is that these locks and unlocks have to have these sync instructions, which means anything prior to the lock should have completely finished before getting the lock, and something after the lock cannot start. Correct. And after you unlock, everything that happened in the critical section has to be visible to everybody instantaneously. If you have unlocked, it automatically implies that whatever you did within the critical section is visible to the world. That is the property of the fence instruction, because what I'm telling you now is that the instructions that are used in the lock and unlock are these sync instructions which have a built-in fence. All right, so the key term here is a built-in fence. Is this part clear? That any lock and unlock also needs to have a built-in fence to establish this ordering, right? Ordering is important. Now, as we have discussed, a program is data race free or properly labeled if every shared variable has its associated lock, and before accessing it, you lock it and then you unlock it. That is the idea, right? So if a program is data race free or alternatively properly labeled, same thing, then the idea is that the claim is it will have a sequentially consistent execution on all machines regardless of the underlying memory model. So this is a very, very powerful result. Let's not look at the implications of it. The proof is, by the way, there in my book on advanced computer architecture, but let's look at the implications. The implications are very clear. The implication is that when I'm writing a program, I know my shared variables. If every shared variable, I'm wrapping it in a critical section where every shared variable is protected by the same lock. And the locks internally use these sync instructions because that is ensured by the locking library. If let's say you're using pthreads, the instructions that pthreads will use will be these sync instructions only. So then you are establishing some order. So the claim of the theorem is that if your program is written in this manner, then regardless of the memory model followed by the underlying machine, regardless of it, your execution will be sequentially consistent, which essentially solves your problem, because we told you sequential consistency is in general not possible because it is too impractical, it will slow down your system badly. Fair enough. So that is why you have a weak memory model that allows you to reorder accesses to different addresses, because for the same thread, it doesn't matter. See, consider a thread. You do x is equal to 1, y is equal to 1. Let us assume they are reordered. Does it matter? It doesn't matter. But in a multiprocessor context, it actually matters because it tends to violate sequential consistency, which is our correctness criteria. But now what is being said is that if you have locks, then, so of course, we'll slightly tinker with the definition, but that is better left to a computer architecture course. Your execution will appear to be sequentially consistent. Or put it in another way, an external observer will not be able to make out whether it is running on a weakly consistent machine or a sequentially consistent machine observing the outcome. All right, and that is what you needed. So that is good. So the main idea is that a data race was a concurrent and conflicting access, but because we have these fences, we allow a dependence to form. Because anything within a critical section has to happen before the unlock. The locks and unlocks themselves, so all synchronization instructions between them are sequentially consistent. All right. If I just considered accesses to these sync or atomic variables or atomic locations, those will be sequentially consistent. All right. So that is the guarantee. And if that is the case, then the entire execution will appear to be so, which basically means that if you just correctly place your fences, which are also known as memory barriers in some geographies, and the Linux kernel tends to use the term memory barrier as opposed to a fence, but they are the same thing. All right. So if you do that and you just wrap them in critical sections, then you are done, right? Nothing else needs to be done. And in terms of an external observer, or let's say some other entity that is trying to verify the execution of your program, it will appear, the key word is appear, all right? It will appear to be sequentially consistent, which means that you can then, it is easy to reason with programs that are sequentially consistent, because somehow a parallel execution is being reduced to a sequential execution. So it is easy to reason with such programs and executions. All right. So this is the crux of our result, and this is by far one of the most important results in the area of concurrent systems. Is that clear? So if I were to give you an example, so locks, as I said, use atomic operations or instructions, and they have these built-in fences. So it's not very hard to see that, let's say, within two critical sections, if the same variable is accessed, an order is being created. They are not concurrent anymore. Why? Because I have a write here. I have a synchronizing instruction here. Then an order is being created because from the definition of a fence, the fence completes only when everything before it completes. Then, as I said, across fence instructions, right, they are, if I just consider fence instructions by themselves, they are sequentially consistent. The hardware needs to ensure that, which means there has to be an order like this between this, because you unlocked and this one locked. There has to be a happens before order. Subsequently, what I said is that, again, from the definition of a fence, whatever happens within a critical section has to appear to happen after the fence. In this case, the nearest fence is the lock. So there has to be a happens before here. And given that happens before is a transitive relationship, there is an order between x is equal to 1 and x is equal to 2. All right. So the main aim over here is to actually insert these fence operations at the right places. And at the right places, you know that you associate every shared variable with either one lock address or multiple, and you just lock it. That is all that you need to do. So given that we have reached this point, we have some understanding of memory models, we have some understanding of fences, and we also know that the memory model followed by your machine, be it an Intel machine, ARM machine, doesn't matter as long as your program is properly labeled, or data race free. Same thing, right? Where the definition we have given. If that is done, the architecture's memory model does not is not relevant. Next, what we will discuss is progress guarantees, that once we are sure of correctness, we will look at whether the operation will ultimately finish or not. Right? Just being correct is not good enough. For instance, if you consider a traffic signal. In a traffic signal, no two perpendicular directions can be green at the same time. That will lead to a collision. So this is a safety property, which means something bad will never happen. But this does not say that a red light will ultimately turn into a green light. That is a liveness property, which says that something good will always happen. So next we will discuss liveness and move on to more advanced topics in the next lecture.